Okay, so our next integration technique is called numerical integration. It's a method for finding the definite integral, so on an interval from a to b, of the area under the curve of some function is represented by taking a set number trapezoids along that interval. So a to b would be the interval prescribed by the definite integral. And in this case, I've set up 1, 2, 3, 4 trapezoids. I could have set up more than that. But the important thing is that the trapezoids reflect endpoints that actually touch the curve prescribed by y values. Sketch these in. That come from whatever the function of x is, and that would be this function of x. So the trapezoidal rule is a formula that lets me approximate the area under the curve, the entire area, by finding the average of the areas created by the sum of the areas of the trapezoids. Okay, I said that badly. Hopefully the meaning came through though. And you can see that it's not a requirement that the trapezoid be less than, so it's not a lower trapezoid and an upper trapezoid. I have a seemingly equal trapezoid here. I have a greater value here, 2 lesser values, but the average of these 4 trapezoids should approximate or will approximate the area under the curve on that interval quite well. So let's look at how the formula is built. Okay, so for the purposes of full disclosure, I should tell you I'm not actually going to build it from scratch. I'll provide that on my site. But for the sake of time on the video, I'm going to give it to you, and we'll use logic to kind of see how it probably, or how it does, in fact, describe the area or approximate the area. So I know that this is what I'm looking for. I'm not going to write that part down, so I'm going to say this equals the sum of the areas of these 4 trapezoids. So we're going to need some notation, and we're going to need a formula for a trapezoid. So let's start with the formula for a trapezoid. We know that the area of a trapezoid is length side 1 plus side 2 divided by 2. So we're actually looking for the average height across the trapezoid times the base. Okay, so that's our formula for a trapezoid. Let's look at some notation so we can convert this into values that we can use. If we say that A is our XO value, then I know that this value would be X1, this would be X2, this could be X3, and B then would be X4. So now I have X values that I could put into this value. The height of this line would be the F of XO. This would be the F of X1. The height of this would be the F of X2, F of X3, and this one would be the F of X4. So now I have a way to represent heights, or S1 and S2, so side length or edge length, however you want to describe the formula. I would say then that the area of this first trapezoid would be written as, well, the heights of the lines, just this part, I would write as, let me back up here, give me lots of room. I would write the heights as the F of X1 plus the first height, the F of X0, and the average would be divided by 2. So divided by 2. And then I would have to multiply this by the base. And I'm just going to write base here. I'm not going to write X1 minus X0. Though I could, but it works for me to not do that, at least in this demonstration. So now let's add the area of the second trapezoid. So that would be F of X2 plus the F of X1 divided by 2 to get the average plus its base. Then the third trapezoid, same thing. And last but not least, let's see, let's use purple. Ooh, that B barely fits in there. All right, now I'm going to do a little bit of factoring. So if I imagine this is just one long polynomial, and it is, and I want to factor parts out, well, what's common to all of them? They all have a base, right? And so I could say this is x1 minus x0 plus x2 minus x1 plus x3 minus x2 plus x4 minus x3. Or I could be a little bit craftier, and I could say that the sum total of all the bases is equal to b minus a, so whatever b is minus a, divided by however many partitions there are. And in this case, there are 4 partitions. Okay, so I've taken care of the b's that are repeated or duplicated. They all also happen to divide by 2, so I could definitely factor out a 1/2. And I'm not going to combine these. In a minute, I'm going to do something with this. So I'm going to keep it as 4 times 2 and not convert it to 8 ever. Now, what's left inside? Well, let's look. I have f1 plus f of x1 plus f of x0. Okay, so let's go ahead and put the f of x0 in the front just because, you know, let's work methodically across the base. Plus, well, I have an f of x1, but I have another one over here. So I've got 2, by combining like terms, f of x1s plus, well, I'm taking care of this one, just doing notation, f of x2, and I have another f of x2, so that's 2 times the f of x2 plus 2 times the f of x3 plus, there's only one f of x4 left. So notice that the first value, my a value, my f of a, written as f of xo, is only represented once. My last value, my end point, f of x4, is only written once, but every other length is written twice. And that makes total sense because each trapezoid shares on these insides. The orange and yellow trapezoids share x1, the green and orange trapezoids share x3, and so on. So now I think I can make a formula that generalizes this whole idea, right? So in this case, remember I had a 4 here, but I think I could write b minus a divided by, well, 2, because they all had a 2 times the number of partitions. In this case, there were 4, but if I had divided by 5, the formula would have still worked out exactly the same, except I would have had 5 partitions. So to generalize the whole thing, we're going to go with an n. And then inside, well, we're always going to have our f of xo, plus we're going to have 2 times the next one, plus we're going to have 2 times the next one, plus 2 times the next one, on and on and on, until we have 2 times the second to last one. Right? That's how we say that. Plus 1 time the very last one. Right? And so the last partition is represented by n. In this case, the last partition was represented by a 4. And so all I've done is replace n for those. So let's take this and copy it up to the beginning. See if I can do that without making the whole thing jump around too much. All right, so we're going to copy this. We're going to go back up to the beginning. There you go. Okay, so let's do an example. Let's estimate the definite integral 1 to 3 of 1 over x dx. Okay, and we're going to use the trapezoidal rule where n, we want 4 subintervals. So first we need to find the endpoints. We know that xo is 1, and we know that x4 is 3. But we don't know where x1, x2, and x3 fall. But we can use the change in x from our formula right here. We can say the change in x is b minus a divided into n subintervals. So b is 3 minus a, which is 1, divided by 4. So we have 3 take away 1 is 2, so 1/2. So each subinterval is going to increase by 1/2. So xo is 1. x1 then would be 3/2. 1 plus 1/2 is 3/2. x2, well, let's write it up here. x2 then would be x1 plus delta x plus 1/2, which equals 2. x3 is x2 plus 1/2, which is 5/2. And x4, we already know, is 3. So now we have all of our x values. Now let's put together the formula for the trapezoidal rule. So the approximate integral is equal to b minus a, 3 minus 1, over 2 times n, 4, times the f of x1, so we want the f of 1, plus 2 times the f of x2, which is 2, the f of x0 is f of 1. The f of x1 is 2 times the f of x1, which is 3/2, plus 2 times the f of our next value. I'm going to avoid using my 1s and 2s because I get my tongue all jumbled up. Good Lord. Apparently I even get my fingers jumbled up with all these notations. So following 2 is 5/2. And then my last value is just plus 1 times my last value. Okay, but what is that? Well, 3 minus 1 is 2 divided by 2. That just disappears out of the formula. So I have 1/4 times, well, 1 over 1 is just 1, plus 2 times 3/2. 1 over 3/2 is just the reciprocal, 2/3, plus 2 times, again, the reciprocal, or 2. 1 over 2 is 1/2, plus 2 times the reciprocal, 2/5, plus 1 over 3 is 1/3. So a little arithmetic by way of calculator, I get the approximate value 1.16 and 6 repeats. So this is the approximate value of the definite integral on the interval from 1 to 3 of 1 over x dx. Now, as a little side note, we're going to learn later that whenever we're looking at 1 over x, because remember, we're not able to integrate this using any of our earlier rules. We have the natural log of 1 over x dx equals, I'm sorry, not the natural log. We have the integral of 1 over x dx equals the integral of x to the minus 1 dx. And if I use my rule, that would say I have x to the minus 1 plus 1 over minus 1 plus 1, which leads to 1 over 0. And that obviously isn't the answer we're looking for, or the a valuable integral. You're going to find later that while this is not possible to use this rule, that another form of integration tells us that this is the natural log of x, or rather the natural log of absolute x, and then because this isn't a definite integral, plus c. So let's use that, or let's look at that. In this case, I would find that the integral on the interval 1 to 3 of 1 over x dx would equal the natural log of 3. And if I put that into my calculator, I get that that is 1.0986 and it goes on forever. So even though in this case it's very approximate, the value is not exact because I'm dealing with the natural log, you can see that it's a pretty close approximation to what I got using the trapezoidal rule. So let's just recap real quick. The trapezoidal rule, which I went farther to define it or to write the rule than I thought I was going to. I just got carried away. I thought I was just going to show it to you and talk about it for a minute, but I think it was valuable to see it. And that the way to use the rule is to use A as XO, B as X4, and the intervals, the number of intervals, plug it into the formula, find your X values that can be plugged into your function to find the height values for each of your trapezoid edges, and then just pluggy-chuggy get the answer.